Hello, everyone. Today we're going to talk about what is called concavity. Concavity is an application of the second derivative this time. Okay. So let's start with some definitions. We say something is concave up on an open interval if f prime of x, f prime is increasing on an interval. We'll call it I. We say it's concave down if f prime of x is decreasing on an interval I. Right. So we have to be very careful here. This is f prime increasing. So to see if something's increasing, we look at the derivative. But we already have f prime. So I'm looking at f prime. I'm looking to see if it's increasing or decreasing. So that's saying we're taking that derivative again. So we call this the second derivative test. So we're checking to see if the derivative function is increasing or decreasing. So we look at f double prime. So if f double prime is greater than 0, f is concave up. If f double prime is less than 0, f is concave down. Let's look at some examples. Let's start with y equals x to the third. So let's first take this second derivative. Even though we know the shape already, we can just say if x to the third is concave up or concave down. But let's do it with the derivative. If I want y prime, I'd have 3x squared. If I want y double prime, I'd have 6x. So very clearly, to make this second derivative 0, x would be 0. So we want to see what happens at 0. So I want 0 equal to 6x, so x is definitely 0. Okay? So let's pick a negative number. If I take a negative number and plug it into 6x, it's going to be negative. So sometimes I like to write this like this. Negative sign, and I circle it, saying it's the second derivative negative when it's less. If I plug in a positive number and multiply it by 6, it's going to be that same positive number, but multiplied by 6. So it's going to stay positive. So we say x to the third from negative infinity to 0 is concave down. And then when it's bigger than 0 is concave up. And then we'll come back to that point 0. We're going to have a special name for it in a second. Okay, let's look at one more. Let's say we have x squared. And just by looking at the shape of x squared, it's a u. The shape is always concave up. So that's the best way to think of what concave up looks like. If it's shaped upwards, like x squared, that's concave up. If you had negative x squared, that'd be concave down. It's shaped downwards. So say we have y equals x squared, then y prime is 2x, y double prime is 2. So if I have y double prime is 2, it's always going to be 2. meaning it's always positive since 2 is positive. So we'd say this is always concave up. So now let me give you a definition. So we're going to say a point where concavity changes is called an inflection point. So if we go from concave up to concave down, or concave down to concave up, then we're going to have a change in concavity. So we call that a point of inflection. Let's look at an example of this. Let's say we have f of x equals x to the third minus 3x squared plus 2. If I want to find f prime of x, it would be 3x squared minus 6x. If I want to find f double prime of x, we get 6x minus 6. And then we set that equal to 0. So we have 6 equals 6x. So x equals 1. So the sign will be negative when x is less than 1, is 0 at x equals 1, and positive when x is greater than 1. So when x is less than 1, the sign is negative. So it would be concave down. At at x equals 1, it's 0. So we would have an inflection point. And it's positive when x is greater than 1. So it would be concave up when x is greater. And it's going to be an inflection point because we're going from negative to positive on that second derivative. Okay. We have some special cases. Let's say we have y equals x to the fourth. We want to know, does this have an inflection point? Let's take a look. If we want to find y prime, we'd get 4x to the third. If we want to find y double prime, we're going to get 12x squared. Okay. So we get 0 equals 12x squared. X would be 0. Make our number line with 0. Okay. So let's plug in a negative number. If I plug in any negative number and I square it, it is going to be positive. If I plug in any positive number and I square it and multiply it by 12, it's still going to be positive. So no, it does not have an inflection point. So just because we can solve the second derivative and we find a value, it doesn't mean that the sign is always going to change. There's cases where there's no change in inflection. And x to the fourth is a great example of that. Let's apply some context now. So let's say we have a particle moving along a horizontal coordinate line. So moving along the horizontal coordinate line. Remember, this means positive to the right with position function. We'll call it S of t equals 2t to the third minus 14t squared plus 22t minus 5, such that t is greater than or equal to 0. We're going to find velocity, acceleration. So velocity, acceleration. We're going to describe motion. Okay. So let's first find velocity and acceleration. So velocity, we'd have 6t squared minus 28t plus 22. So that's just our first derivative. We have position, we take the derivative, we get velocity. Okay. If I want to go ahead and factor this, I could factor out a 2, and I'd get t minus 1, 3t minus 11. I'm going to leave that as an exercise to show how to get from one to the other. It's just factoring, factor out the 2, and then you should be able to factor it. Acceleration would be 12t minus 28. Again, we can factor this to 4 times 3t minus 7. Okay. And then if we want to describe motion from velocity, so from our first derivative, we can say when velocity is increasing, decreasing, and increasing. Right. So we want to find these different points. So we start at 0. So we only need a number line in one direction here. Okay. So one of our t's to equal 0. So if I want t minus 1 to equal 0, I'd have t equals 1, give me 0. So we want to look at 1. And then we look at that 3t minus 11 equals 0. So if I have 3t minus 11 equals 0, I add 11. So 3t equals 11. So t equals 11 over 3. So now we do what we did before. I pick a number between 0 and 1, and I see if it's positive or negative. So I'm going to leave these for you to try as an exercise, but I'll give you what you should find. So from 0 to 1, you're going to get any positive number. So it's going to be increasing. Between 1 and 11 thirds, I recommend just picking 2. You'll see that it's decreasing. And then pick a number bigger than 11 thirds. And again, you'll see it's increasing. So we want to know what that means with relation to this particle. So we're moving along the horizontal line. We found when we took the first derivative to see when it was increasing or decreasing. So what this is really telling us in the context of this problem, since we're moving along this horizontal line, think of this as going right, going left, and going right. Okay. From acceleration, when we set it equal to 0, again, we're going to start at 0. And then if we set 3t minus 7 equal to 0, we'll see that you get 7 thirds. Okay. So it would be concave down here. So if you picked 1, plugged in a 1, that's definitely a negative number. If you pick 3, let's say, that's going to give you a positive number. So this would be concave up. So in the context of the problem, This is telling us that we're slowing down. And here, we'd be speeding up. So I want you to fill in all the details here. Pick actual numbers, see it's increasing and decreasing. Actually set those first consecutive derivatives equal to 0. I omitted those steps there, but I want you to go back and try those. And then try and follow along and see if you agree with where I'm increasing, decreasing, and increasing, and where I get concave up and concave down. So that's going to be it for today's class. Please go ahead and try some of those practice problems. I hope everyone has a great day, and I'll see everyone next class.